C safely. Even when they use these unsafe operators, they use them in certain coding styles that are perfectly fine most of the time. And in the remaining C programs, there are only small portions in which the operators are used unsafely. Okay? Essentially, most of the C code out there is type safe, is memory safe. The problem is the C type system itself is not able to see that. It's not able, it sees, your unsafe use. The use of unsafe operator says the program is not type safe, or essentially it doesn't say anything. So here's the idea of CCured. We're going to enrich the C type system. We're going to enrich it to the point where it becomes type safe, and it will look at your uses of unsafe operators. So we'll be able to distinguish the good uses from the bad uses. Okay? And we're going to design a type inference algorithm as well, one that will take existing C programs and infer this additional information that you need for the CCured type system. Step number 2, because we don't really hope that this idea, this part, step number 1, will handle all programs, we're ready to come in with runtime checks. And in essence, we're going to design the type system to point out to us the portions of the programs which require additional checks that could not be verified statically. For example, array bounds checks, or even heavier dynamic type checking. Step number 2 is essential for getting us to getting the system, the CCured, usable on large existing code. But it also means that we're willing to take a performance hit. But I think this is okay. So one of the CCured premises is that today, with the constraints of today, it's okay to sacrifice some performance and to buy safety in return. Okay? For most programs, maybe not all programs. But as hardware improves, I think it makes sense for more and more applications to trade off a little bit of performance for safety. What are the goals we started with? We wanted to support existing C code. We envisioned the system to be used as a source-to-source transformation. We wanted it essentially to write a replacement for the compiler, for GCC, or the CL compiler, Visual Studio. And this is what we envision. You just take your program and run make with CC equals CCured, and all will be fine. Well, I will tell you right away that we didn't succeed to make it quite like this. And what I'll show you essentially has the feel of porting. So there are changes that we need to make to the C program. We had efficiency goals, because we were looking around and saw all of these techniques that in research world, or Purify, Bounce Checker, Valgrind. Now, purely dynamic techniques, which are good because they don't need source code, but are bad in terms of performance. And we thought there's no reason why you should be 10 times slower, provided you have access to the source code, and provided that our premise that most of the C program is actually perfectly fine. We had a goal of 50% overhead, which we were there, pretty much. We wanted this to be not only more efficient than Purify, but more effective as well, because we have more information. We have the source code. Purify does not. And in fact, we succeed there. We find bugs that Purify does not. We envision this, and we still hope that such a system could be used for production code, not just in the lab, as like Purify. Yes?
What was the goal if you didn't need to insert any dynamic checks?
If I didn't need to?
Yeah, if your program type inference said everything's great, presumably you had to change some other things in the underlying.
Yeah, I would have to throw out pointer arithmetic and arrays.
So how much were you hoping the efficiency would be off in that case?
My initial goal was that I'm going to pay 30% for bounce checking. This is based on some measurements I did before I started this work. In a tight loop, this is how much you lose, but most of the time if you average it out over the program, probably it's better. I will tell you right away, if you're curious, that we do have programs that are 80% slower, depending on the workload, depending on the program. Most programs actually are below 50%. Okay? Let me point out what do we want to cure in this version of C. We're going to look at pointers and essentially memory safety. We want to prevent dereferencing a non-pointer, either null or just number 5 disguised as a pointer. And related problem, we want to prevent you invoking a non-function. This issue is complicated by casts or hidden casts due to union types. We want to obviously prevent you from dereferencing outside of object bounds, like prevent buffer overruns. And here we have to deal with pointer arithmetic and a cast. Now, our goal here is we want to define object bounds in a more refined way than Purify does it. For example, if you have a structure with 2 arrays as 2 separate fields, we consider those as 2 different objects, while Purify simply cannot do that without source information. A secondary goal, or rather one that we didn't pay as much attention to, is memory management. And here we will use a garbage collector for now.
I was curious in your concept of object boundaries. You handle the case. We typically see programmers do something like, well, I'm going to go off and write my own malloc that builds something huge. And I know there are systems in the past that have said, okay, that's the size of the object. And clearly what you're going to be doing is handing out pieces.
Yeah, that's an excellent question. And I have a slide about that at some point. I will handle it, but maybe in an unsatisfactory way, or depending on the point of view. Okay, so let me try to give you an example for leading into what is this new type system going to look like. What I have here is a rather ugly-looking definition for a hash table. It defines a list structure with a data field and the next pointer, and then it defines this vector of pointers to list. Okay, so it's depicted here. This is a vector, and these are the buckets including this linked list, and you have this main pointer pointing somewhere into the vector. My point with this example is that if you look at various pointers declared here, you will notice that some pointers, or you can expect that some pointers will be used in certain ways. For example, this pointer to the list cell, either this or this, essentially the blue pointers in the system. You don't really expect to do pointer arithmetic on them. And you probably won't be casting them. You'll be setting them to null. This would be the worst thing you do to them. So in fact, these pointers are pretty much like references in a type-safe language. They could be null, but otherwise they're fine. Then we have this pointer in here, which you might expect to move with pointer arithmetic into this array. Okay, but otherwise no casting. And therefore this pointer needs maybe a null check and a bounce check. But it's still, in a sense, a type-safe pointer because you know it always points to a list. It points to a pointer to list. But then whatever you store in these hash entries, this data, the type system doesn't help you here. It says it's something, some essentially word there. And maybe you have even different kind of objects there. So these are objects. These are pointers that are of different status than these two. So in fact, CCured classifies pointers according to these 2 dimensions, essentially. Can you cast them? And can you do arithmetic on them? And if the answer is yes to both, you have the most powerful kind of pointer, which is the C pointer. But the point is that you need to use rarely. And we'll have that pointer. We'll add some runtime checks to make sure you use it correctly. The answer is no to both. You have these blue pointers, which you call safe. These are just like Java references. There's no reason why they should be slower than regular references. And then there's this kind of pointer here, which you call sequence pointer, on which you still cannot cast. Therefore, you can count on its type to be accurate, but you can do arithmetic. So you might need to do bounce checking on it. So with this motivation, let me now describe question.
So the 4th thing that's missing from your table would be a combination that you would use in C if you programmed an object for it as well. But you found no use for that here.
I have a use for it. It comes from the middle of the top. Okay, good question. So I'm going to ignore that combination. With these 3, let me just give you a CCured, one slide. I'm going to show here the various invariants that CCured maintains for different kinds of pointers. I'm going to classify those pointers according to how capable they are, how many things you can do with them. And at the bottom line, you should be able to read or write from it, right? Then you can do some arithmetic in addition, or you can even cast it. And obviously, the pointers that you just dereferenced are going to cost less. So I'm going to classify them how much it costs in terms of runtime. The simplest CCured type is the safe pointer. So I should point out that we actually extend the C syntax with pointer attributes. And these are read just like C types from right to left. It's a safe pointer to a tau. And I'm going to use on this slide the convention that the dark blue is the actual pointer and this light blue is the data it points to. And the main point here is that the pointer is one word. Might be 0, but otherwise, you know it points to a valid tau. So the layout of this memory block it points to is a valid tau. And it contains pointers itself. Okay. Then, if you want to do arithmetic, you have these pointers which you just increment. You just go forward, P++ with them. And for those pointers, we need an additional word of metadata. This is data that CCured maintains and uses for its runtime checking. The programmer cannot really mess with this data. So this one, you need the end of the sequence in which you are pointing, and you can only go forward with this pointer. Turns out this is a very, very useful special case. But the full power of pointer arithmetic you can get with a sequence pointer, which has 3 words, has a beginning, an end, and then an actual pointer. And for all of these, if the type system says you point to tau, then you actually point to a tau. What if you want to do arbitrary cast? Well, that's when we have this all-powerful wild pointer, which is significantly more expensive. In terms of space, you need one additional word with the pointer itself, but you need some metadata with the area in which the pointer is pointing. You need the length of the area, and more importantly, you need some tag bits. Okay? So at this level here, so essentially CCured kind of splits the world into a statically typed language where the type system is accurate with respect to the runtime, and a dynamically typed language. And this is dynamically typed in the sense that we have one bit of tag per word of data here telling us whether it's a pointer or not. You can't really store more information for these pointers because really you can do arbitrary casts with them. You can count on their type. And there's one more point here. If you look at what's here, this is like what you have in C#, in Java, or in ML. These are the regular pointers, and these are arrays, just with different representation. This gives you the power of arrays in C# with bounds checking. What you have here is more like maybe Lisp. It's a scheme. And essentially CCured will take your program and split it into 2 parts. The statically typed one, which is like, will essentially convert your program into C# and convert the other part of the program into Lisp, and will make these things work together. There's one constraint that's very important. These 2 worlds cannot touch each other in arbitrary ways. It's okay to have pointers from the statically typed world into the dynamically typed world, but it's not okay to have pointers the other way. This is pretty standard in systems that try to have this combination of types. And I will have a couple of slides showing you exactly the why we have to avoid this. Okay? So now, based on your programming experience, in an average C program, how many pointers, static count, you think are safe, sequence, or forward sequence?
80 to 90% would be my guess.
Safe. Right? And between, this would be a sequence here. Forward sequence and sequence, you might expect that programmers use a lot more forward-going pointers than just pointers that go both forward and backwards. So in fact, with this simple definition of safety, essentially pointers that are never cast, never incremented, either themselves or pointers to which they are assigned throughout their lifetime. Okay? Between 40 and 95%, depending on the programming style, and sometimes depending on the size of the program as well. Whether you use arithmetic, depending on whether you use arithmetic, you have between 0 and 20% for going pointers. And these more expensive sequence pointers with 3 words are kind of rare.
So one thing I didn't understand, that the sequence F sequence, if you violate the bounds, I'm assuming that these arrays are not statically sized. You can't determine a compile time the size of those arrays.
Right.
So if you violate this, that is the correct assumption. At compile time, you can't determine the size of those arrays.
Let me go back here. Sometimes I can determine the size. But the point is that this pointer here, let's take this general case. This was born into an actual array, either allocated by malloc or statically allocated. But then it was passed around. And that's why it needs to carry with it this information.
So they're statically typed, but there is the notion of a runtime exception possibly
Right.
occurring when
The tau is determined statically,
Yeah.
but the bounds are carried at runtime.
Okay.
In rare cases, I can predict them statically, but in general, they need to carry information with them. The forward sequence pointer, there are two runtime checks. I think this is in next slide.
Yeah, that's fine.
So this is a few more details about the runtime checks that I need to do. For safe pointers, I need to do null checks. Okay, what you expect from C# or Java. We could have, and we experimented a little with another version of safe, which is guaranteed not null. That's a fine addition. The other pointers can actually contain not just null, but any integers. You can disguise an integer into an F sequence pointer, essentially because you have 2 words of metadata where you can encode that this is not a pointer. So they need a more powerful notion of null checks, which is to prevent using non-integers. All non-safe pointers have bound checks, including sequence and including the while. For the forward sequence pointer, you only need an upper bound check. For the sequence pointer, you need 2 bounds checks. While pointers maintain type tags, which you have to check on reading. Actually, only when you read expecting a pointer, you have to verify that's a pointer. And every time you write, you have to set that bit according to whether it's a pointer or not. You can downgrade the pointers in the statically typed world to safe. Like if you have a pointer that in some contexts is used with arithmetic, but now it's going to only be used safely, you can downgrade it to safe, essentially cast. And the system will infer exactly where this cast ought to be, but the cast is associated with a bounce check. An important point here, forward sequence pointers are checked at runtime that only go forward. If you just do P++, this by itself is not a guarantee that the pointer goes forward because of overflow. And in fact, in the first version of the system, we didn't have this check, and it was possible to construct an example where you violate, where you essentially segfault. I have not told you about some other checks we need to do. We prevent stack pointers from being saved in the heap or in the global variables. And this turns out to be actually a minor annoyance. Very few programs actually save stack pointers into the heap. The system will allow you to save stack pointers downwards into the hotter areas of the stack. And that's typically used when you pass down, or do call by reference, pass down the addresses of your local variables. Okay? Are there any questions on these runtime checks?
So it's not clear. Sorry.
Oh, sorry.
I was going to say, it's not clear when you say maintain type tags, what do you mean by that?
That's my question too. 1 bit per word.
There's 1 bit per word. Each word in the data has 1 bit associated. The bit encodes whether the corresponding word is a pointer or not.
Is that bit actually associated with the address, or is it actually associated with the wild pointer that points to it?
It's with the data. If I go back, each bit here corresponds to 1 word of data.
Okay, so does that mean in practice you basically have a bitmap sitting on the side for all of memory?
It actually, in our current version of the system, looks exactly like this.
Okay.
When you allocate this area, whether it's statically, compile time, or with malloc,
Okay,
we
all right.
set that.
Okay, so it's associated with the data.
Mine's just an answer on that. So it's not 1 bit per word of memory in the entire memory space. It's just the object of the type being pointed to by the wild pointer.
Right. Those objects living in the dynamically typed world have 1 extra bit of data. Okay? One of our goals will be to reduce this to a very small portion of your program.
How does that tagging scheme work with things like e-copy and so on? I mean, it's clear that the static stuff, you know the size of everything, and the fact that your pointers are bigger is no big deal.
Right.
But I'm concerned about what happens when people actually try to do data motion in the heap.
So we recognize certain functions. So whenever you call out of the system into the runtime library, we have wrappers and essentially specifications for a lot of those functions. And those can detect whether they are working on dynamically typed data or not, and they can do the appropriate stuff. This is messy here. So one of our main goals will be kind of reduce this.
What happens when you start dealing with arrays of pointers? and pointers to pointers.
Yes.
It seems to me like now you've got 16 possibilities running around.
Yes. It's not that bad. The key is in writing down the type, right? You can have a safe pointer to a safe pointer to tau, or you can have a sequence pointer. You can have combinations, but it's fairly easy to read what you mean. I'm not sure then what the question was.
Well, I was just thinking that there could be some interesting implications if you, say, had a wild array of safe pointers.
Yeah, that's the next slide.
Okay.
Well, not quite this, but the next one. There are two complications with wild pointers. Essentially, I'm going to explain how can these two worlds really touch. Is it possible to have a safe alias for a wild? Okay, so code like this. You declare a safe pointer to T, S, and you declare a wild pointer to T, and you pass it, you assign it with S. This is the picture of what this will look like, right? S points to a T, and then W also points to a T, and probably the base points to something that encodes F. T. So first, the first fishy thing in here is wild needs some metadata, and safe doesn't have it. So how are you going to put this assignment? But not even looking at this issue. This is bad, right? Because you could write this code here. W being a wild pointer, you can cast it to whatever you want, to the tau prime, and that will allow you to write random stuff in here, essentially invalidating the static assumptions that S has. So essentially you have, your good hand working the same place with your bad hand, and they kind of mess each other. So you cannot have this if you want soundness. So no aliasing. Never assign between wild and safe. Essentially, if you have something like this, CCured will insist that this be wild itself. And here's the slide about your question. Can you store safe pointers into these dynamically tagged areas pointed to by wild pointers? So P and Q are two wild pointers, and they think they point to a safe pointer. This you cannot have, because these being wild pointers, you cannot control statically what gets written through them, right? And when you say that something is safe, there are some static guarantees that you must maintain about it, okay? So the rule is wild pointers must only point to areas containing other wild pointers.
Could you add checks to the wild pointers to make sure that they don't violate the invariant, such that you can treat the other things as
yes, you could. In fact, there's a research group in Japan trying to do that, but so far it's much more expensive. Right. We do have a pointer type, which I'm going to reveal soon. Ruston kind of alluded to, which is going to solve some of these problems. But just to summarize with the wildness, okay? Wilds contaminate the program very rapidly, because if you have a wild pointer typically arising out of a bad cast, or maybe a programmer declaration, it spreads to all of the pointers to which it is assigned, and from which it is assigned, and to all pointers it points to. All data structures living in dynamically typed areas must contain only wild pointers or integers or scalars. Okay? This is really, it's not the cost of the wild pointer that's really a problem. It's the fact that if you have one of these wild pointers, it spreads rapidly. We've done quite a few large programs now. And it seems like the magic number is the first thing you run it, you have 40% of these. Due to some bugs in the code, due to some problems with CCured not understanding always what you're doing, the first try, CCured comes out, you have 40% of these pointers. This is how much it spreads. So we need a way to reduce the wild pointers, and we need to attack the problem where they arise. There's no way to fix this. These are needed for soundness, but you can eliminate them at their origin. Right, the bad cast. So we need a better understanding of cast. This is what I'm going to spend the next few slides on. If you look at casts, you can actually classify them. Well, but here I'm going to take the liberal notion that a cast is really any assignment, a function call, function return. And 63%, this is static count, of these assignments or casts are between identical types. There's no problem here. 34% of them are what we call upcasts. So in C# or Java, this would be casts out up the class hierarchy. A pointer to a large struct is cast to a pointer pointing to a prefix. I'm going to explain this further. So we better handle these. 2% are downcast, pointing in the other direction. These are the checked casts of Java or C#. And 1% are really nothing we can tell about the relationship between the two types. Typically, at the exit of a memory allocator, we have something that looks like this. And this data is really, and we measure this over many programs, and it's similar to what other researchers have obtained. So I think it's pretty accurate picture of C programming. Let's look at upcasts. Okay, so an upcast, let's take a look at this data type here. Data event has 3 fields, and we call this a physical subtype of this shorter struct. Okay, and if you think of the layout of classes in object-oriented programming, then this would be a superclass of this. Casting in this direction, it's an upcast, and it's perfectly fine. So here's a picture. You have a data event object somewhere in memory, and a safe pointer to it. It's perfectly fine to cast it to an event pointer, because this event pointer will essentially just see a prefix of the data. But whatever you can do through this new pointer will still agree with the invariance of the data invariant. Okay? So this is an upcast, and in fact, the CCured type system is built around this notion of physical subtyping, so you won't even see complaints about this.
Is there an implicit assumption that these two classes really do have the same invariance, that the data structure layout isn't just coincidental?
No, CCured does not look beyond the typing declaration. But I would point, it's surprising how often this arises. It's surprising how many times C programs program in object-oriented style, essentially.
Yeah, I was just thinking, wouldn't there be a way to essentially write your code to work well with this system so that, say, for example, instead of needing a wild pointer, I declared a union, which then allowed myself to not have to work with a wild, but instead now I've got a sequence, or a sequence both ways. And say is a trivial example, say a IP packet. I could treat that as 1,500 bytes, or I could treat it as an IP header plus other thing. But as long as it stays the same overall size, then it's okay.
Right. So CCured will recognize physical subtyping in all forms of shapes. I mean, it flattens out the types and then compares them, including padding and all that. So that might answer part of your question. The other part is, I should point out, CCured does not care about scalars. Okay? So if you have two types that look differently, they're same length and have arbitrary scalars, including floating point, you will not complain, because it's not going to mess up pointers. It's only pointers that have to be aligned perfectly between the event data type and data event.
You mentioned object-oriented programming. Any plans, or have you applied to C++ programs?
Yes, I will get to that. And the answer is yes and yes. Okay, so let's look at the other story. Upcasts are an easy problem. I should point out that the physical subtyping notion is not our invention. It was actually introduced by a group at Bell Labs. Tom Ball was part of that. A downcast is going in the other direction. It's not quite as not used quite as often as upcast. But here's a case. You have P, which is of type T star. It's a pointer. You cast it to void star, typically to put it into a hash table or some other container. This is an upcast. Okay? Take the view that void points to the empty type. It's really the prefix to all types. It's perfectly fine, meaning that if you can ever use a void star directly without casting, which you can't do any harm. So, but the only way you use a void star pointer, is to cast it back, hopefully back to the same type. This is a downcast. Okay? And 20% of the pointers in the program are void star. And the only way you can use a void star is to cast it. And all of those are downcast. So you better have a way to handle that. And our way to handle it following a number of proposals, a few of which were of the flavor of parametric polymorphism. Okay? We discovered that doesn't really work in C. Programmers don't program in parametric polymorphic style. Much more often they have arrays whose elements have different types rather than arrays of uniform elements. So we settled on a fourth kind of pointer, CCured pointer. It's called a pointer with runtime type information, and I think this is what Rustin was kind of leading to. Essentially, we're going to carry with the pointer some information about its type. Okay? So here's how a runtime type information pointer, RTTI we call it, arises. You have this pointer to the subclass object, data pointer, and you cast it, upcast, perfectly fine, into an event, a pointer to event. However, unlike before when the cast was just cast to a safe pointer, now you're going to detect that you eventually need to cast this down. So you need to store its information. And you know that because this was a safe pointer, you know it's a data event or a subtype of it. So you stick a stamp on it saying this is a data event. And the pointer travels like this with the metadata until it gets to the downcast. And at that point, we insert the runtime check. Okay. This mechanism turns out to be handling void star pointers very well, as long as you cast them back to the type where they came from, and each individual pointer will carry its type. And it also supports programming in object-oriented style very well. This slide is a bit busy, but the essence is that we have a supertype figure with one virtual pointer in it. This is actual code. People write object-oriented style this way. You have a circle, which is a subtype. It has the virtual method pointer at the first element and then the radius. And here's how you use it. You declare a pointer to a figure, and then you invoke the area method on it. And here's how you write the circle area. The point is, you get the figure in, and the first thing you cast it to a circle. And you know you can cast it to a circle because of the invariance you're maintaining about where you put the pointer to circle area in which of these objects. This is a downcast here. CCured will detect that. And it will say, the only way I can allow this is if I can check it at runtime. And that means that this pointer has to be RTTI. From there on, CCured will flow this RTTI requirement to all of the pointers that are connected. And essentially, this fig pointer, being RTTI, will carry with it information and will eventually be able to be cast down to circle. That was the first question.
So, my understanding is that when C++ stores RTTI, it stores it with the object rather than with the pointer.
Yes. So that's a good point. This is a design decision based on our observation that it's in C, it's better to avoid changing the layout of the memory you're pointing to, and better to move the changes, to concentrate the changes to the top of your data structure. This is for compatibility with libraries.
But you weren't going to do that, for example, with the layout where you had to add the
for the while.
on the end.
For the while, no, because for the while, you cannot keep the bitmaps with a pointer. The bitmap has to be associated with the data you're pointing to.
Right.
The pointer can be cast to arbitrary things.
Did you to avoid changing the data out, even in the case where you have wild things with these pointer bits, did you just segregate the pointer bits off into a separate address?
We segregated the metadata, but more on that story soon.
Okay.
So does the fact that you basically got a frontier of RTTI being forced, does that mess with things like separate compilation?
In the sense that CCured inference, if you use it on an existing piece of code, is a whole program analysis. And I'll explain that. The way to fix that is to annotate the interfaces with RTTI, which is not hard, but we haven't done for any significant piece of code.
Do you handle RTTI like you would in Java, where you actually have to do walking up a hierarchy or something like that?
Yes. Okay. So you can declare a class hierarchy, a hierarchy of these physical subtypes, and it will do the right thing. But this is good. And in fact, we use this heavily when we do object-oriented C++ even. Okay. But one bit to take from here is that we found that this mechanism is much more appropriate for C than parametric polymorphism. Okay, so now let's go to another big problem. In fact, probably the biggest problem that we face in implementing CCured is compatibility with libraries. We need source code, unlike Purify, and we don't want to really run CCured on all libraries, and many times we don't even have the code. The problem is that CCured changes the data layout of pointers, and if they are embedded in data structures, the entire data structure grows. And then you can't really talk to an existing precompiled library. The first solution, which we still use pretty much most of the time, is to write wrapper functions. And the idea is that you identify functions you're calling. First, I should point out, CCured, whenever it changes the data in such a way that it affects a function, it changes the name of the function a little bit. Adds a mangling to the end to prevent you from unknowingly linking against the library. So the symptom of this is you run CCured and you run into linking errors. We identify those functions and we write little wrappers around them that do two things. One is they do the checking that's necessary to ensure the arguments are okay to go into the function, and then they wrap and unwrap this metadata. We wrote about 120 of those in a kind of lazy manner for C library. Let me show you an example, because there is something in here that's quite interesting. Let's say you have this read function, which takes a file descriptor, a buffer, and its length. This is what we wrote. This is our wrapper. And essentially, it has this call here to this pseudo function that says, I'm going to write to this buffer at least len, sorry. Yeah, I haven't fact-checked my slides. At least len bytes. And then I'm going to do the actual read. But from buff, I only need to take the pointer, not all the additional metadata. The nice thing is that this wrapper tells CCured to do a bounce checking on the buffer. Because otherwise you would be failing into the library. You'd be crashing into the library. And so that's good. It also tells CCured that buff must carry its metadata, must be a sequence pointer essentially, so that you can do here the bounce check. So it tells the inferencer all it needs to know. It's like a summary of read as far as the CCured inferencer goes. The other nice thing is that the inferencer might infer this buffer to be safe, well, never safe actually because of this constraint, but forward sequence, maybe even wild. And you don't want to write 3 wrappers. Okay? So CCured will instantiate this, will inline this, whatever read is called, and then these 2 functions are customized by CCured to what they need to be for various kind of pointer kinds. So this is, for example, what CCured generates automatically if buffer is inferred to be sequence pointer. So the name gets mangled with a Q. This buff is now a structure of 3 words. And this check, write at least, is turned into these 3 checks. We check that it's not null. The base is not null. It's an actual pointer, lower bound. And we check the upper bound. And then we go and call read, passing just the pointer part of it. So it's a little bit of convenience, but the interesting part is that we can add these calls before going out into the library. I should point out that one area of difficulty has been engineering these 2 checks, because in languages like C# and Java, you can do it 1 conditional. It turns out that you need quite a bit more. You need 3 conditionals for C. For example, this might overflow, okay? And that's a big source of problems. In Java, you have all array elements being 1 word. So this is not a problem. You never have overflow if you do the check right. Okay. Wrappers work fine for most simple functions. Think of libc, functions where you pass pointers to bytes, essentially. So you just need to wrap the pointer. You don't need to mess with the bytes you're pointing to. And this goes back to our decision to keep the metadata with the pointer, not with the data. Well, what if you have a function that uses this host end data structure, which contains a string, so a sequence pointer, contains an array, a null-terminated array of strings, sequence pointer to characters, and some integer. Okay? This is how the data structure looks in C. Right? So the 3 words, the string, this string lives in a buffer. And this is the whole buffer. This is the array of strings. Okay, what we did in CCured essentially was to kind of add metadata, base and end for this string, base and end for this array, and then for each pointer in the string. Okay, so if you want to then take this data structure and pass it to the actual runtime function, you'd have to, well, this might not be hard to change, but you have to go and copy this array. And that's bad because you destroy sharing, it's expensive, it's a mess. So what we did, we now have a variant in which we can store all of the metadata separately in a parallel data structure, almost. It's only the pointers in the original data structure that need to have some correspondent data on the parallel, right? So the first word here corresponds to these two words of metadata, the second word to these two. And we have a very nice, actually quite simple, type-directed way for generating this structure. There's one problem, though. This data, I mean, you can't find this data easily from the top of the structure, so we have to add one additional word of just linking this metadata. So this point here points into the corresponding position in the metadata that corresponds to the pointer. Yeah, right? So now the C program is changed so that each write is turned into 2 writes and each read into 2 reads. Essentially, the program will traverse this metadata parallel. The advantage of this is obvious. This part of the data at least corresponds to what the library expects. Okay? So this is how we try to achieve more compatibility. But you would have noticed, I'm sure, that this is not the perfect solution. Because if the library you're calling, library function calling, changes the data in such a way that requires changes the metadata, we still have to write a wrapper to essentially do that. Well, the good news is that in many cases, for the libraries we looked at, we actually only looked at libc and Open SSL for now. You don't need to do this. In general, you need to combine it with wrappers.
Is it correct that you said the metadata was associated with the pointers? So it would seem to me that one of the design choices you could do is to push so that there is the metadata is associated with pointers, but when you get into data structures, actually, you're really associating the metadata with the data itself.
Not quite. Not quite, because this piece of data has metadata only because it contains pointers. This kind of data is not associated really with these pointers. It's associated with the data it points to. So it's always one level up. I'm sure there are other designs. I can't think of
in garbage collection to segregate all the metadata off into a separate set of tables that you can maintain and keep the data itself together. So
the problem is how to find. You need to find the metadata quickly.
Not to map the original data to the metadata.
So we tried hash tables of all sorts, and that didn't really work out well because you need to use this quite often. So that's why we kind of keep parallel structures.
So what do you think of another design point where you did try to keep the metadata associated with the actual object or data that you allocated?
It's very hard. We actually have a version of the sequence pointer that looks like a Java array or C# array. Because it's hard to control mutation of all sorts in C. Like you want to copy these arrays over, and then it was hard for us to maintain the invariant that this field data can never be kind of corrupted.
So the issue is we'd have to sort of know at the machine level what's going on to really track that properly.
Well, I guess what I'm saying is that there are some styles of programming in which that gets in the way. It becomes hard to ensure soundness. It becomes hard to ensure that nobody can touch this piece of metadata. We have tagged unions, which have this problem. The tag is with the union. It becomes quite tricky to ensure that you can't really mess with that. Okay. Let me tell you just a few words about how the inference works. A perfectly fine way to use CCured is to add those sequence safe, and it'll work just fine. But we can actually use an existing code. For every pointer in the program, we will infer the fastest, the best pointer kind on that scale of cost. And the nice thing is that this can be done on linear time, really, because our constraints are so simple. You can do it in linear time, and it's a whole program analysis right now, but it's fast. What we do, we actually merge all of the source file in the program into one file, as convenience for us and then do the analysis for us. Let me show you an example how this goes. You have this sequence of instructions. Pointer A gets assigned to B, which gets assigned to C. B gets incremented and C gets dereferenced. The inferencer will see that B is advanced here, or appears to be advanced, +1. It will infer it to be for sequence, meaning B must carry an end field of metadata. Well, where does it get it from? From this assignment. So the inferencer will propagate the constraint that, well, A must be for sequence as well, to be able to pass in its metadata to B, and so on. So these constraints kind of flow backwards to the origin of the pointer where the buffer is allocated appropriately. But then the inferencer sees C here just dereferenced and can be perfect safe pointer. However, here we have an assignment then, a for sequence pointer to a safe pointer, and CCured will indicate that the bounce check needs to be done there, and C can stay safe. Okay? So I hope you believe that this is actually a simple algorithm.
What did you mean when you said B appears to be there?
Well, because B+1, you don't know whether it's overflow or not. So CCured takes the view that if you add a constant, or do ++, or if you use the brackets to index it, you will infer it to be for sequence, even though it might possibly fail at runtime.
So you're saying the program is not intentionally using overflow in the algorithm. You're sort of assuming.
I have to assume the worst.
Yes.
Okay, so, and if there's a mistake, you're going to raise.
It's going to fail at runtime. Every time I add to a for sequence pointer, I check that I'm going forward.
Yeah.
But the point is, I'm not going to check a for sequence pointer that it's within its upper bound until I use it. But I always maintain that it's above its lower bound. I maintain that. The pointers are not checked until they are used. For a sequence pointer, you can increment and decrement without any check at all times. And only when you try to use it, you get the error. You need this in C because the standard allows you to have pointers slightly out of bound.
What is it? Oh.
Right. I have a similar slide for while, but the story here is so much simpler. You detect that these two are incompatible types, pointer to int and pointer to int, which forces P to be wild and therefore everything to be wild. It's not really that interesting. Oops. Okay, so you do this, and CCured produces this HTML file with JavaScript, which you can use to go and look at your program, click on pointers, and it will tell you that this is blue means for sequence in this interface. It says, well, there's positive arithmetic on it, somewhere where it's not shown, and tells you how it flows to different casts at different points in the program. We use this tool to actually investigate what went on. Sometimes these chains can be, for a whole program analysis, can be 20 long, which is kind of annoying. It would be so much nicer to annotate the interfaces between modules with pointer kinds. Then these chains will be really short, typically one function. So I just wanted to show you that there is some help for you there. What's the real story with wild pointers now? The biggest cost with wild pointers is in library compatibility. In fact, our wrappers don't work really well when you have wild pointers, precisely because we have to change the layout of data, right? So you allocate the file star from the library. If you want to use it as a wild, you have to reallocate that whatever structure the library has for the file to have these tag bits, and it's a real mess. So we've changed the party line on wild pointers, and we now prefer to sit down. Instead of writing wrappers for them that would do some fancy stuff to the data, we prefer to sit down and port the code, essentially. And I'll give you data on actual experiments like that. Sometimes it's really fixing the code. You would be surprised how many times C programmers forget function prototypes, especially for function pointers, because the C compiler lets you do that. We use RTTI. In most cases, RTTI is manual at the moment. You have to add it manually, and you have to describe the class hierarchy manually, and then the system will push the RTTI. We sometimes change the code. It's not really bad code, but it does things that confuses CCured. And sometimes we get tired, And we have this trusted cast thing. Okay, so this is the point in the talk when I'm telling you that this is not automatic and it's not even sound, right? And we had to do this really for, I think, practical reasons. When you port something like Apache, almost 300,000 lines of code, and you want to do it with one undergraduate student in 2 months, you can't really rewrite a lot of the code. This is still not that bad, because I'll show you how many of these we use, and it's about 1 in 1,000 lines of code. If you want to start a security review of your code with respect to memory safety, you go and grep for trusted cast. And it's a starting point. Okay, so I'm going to go now through a number of slides trying to point out a few areas of difficulty for CCured. Like, how does it feel when you sit down? What kind of fragments of code give problems? You can have non-portable code, right? You want to allocate of your favorite allocate of 4 bytes because you know that this pointer is going to require 4 bytes. Let alone that this is bad practice. Well, CCured, this won't work with CCured because T star might well be 12 words if it's a sequence pointer. Instead, CCured points out not such things, but sorry. The next best thing is to use size of T here, size of T star. Right? And this is what people do. That's common program practice. It's still not quite good enough for CCured because it cannot tell the relationship between this T star and this one. So what we recommend you do something that I think is even better for software engineering. You don't write size of T star here. Sorry, size of X. You write size of X because that's what you need to allocate. And this will allow CCured to adapt this allocation to whatever this pointer needs to be. This is easy to fix. You have a few of them, CCured pointed them out.
I don't understand what you just wrote down.
Partly because it's wrong.
Yeah.
There shouldn't be a star here. You're allocating room for a pointer, T star. And you know it was 4. A better way would be to write size of T star instead of 4.
Yeah.
Right? But then CCured would not be able to connect the T star from here with this. It might infer that this is safe. In fact, don't do anything on it. This might be sequence. So we recommend you write size of X here, which will allow, and I think it's even better from a software engineering point of view because otherwise you might get the types confused and the compiler will not be able to tell. But anyway.
What does get bytes return? A pointer to the thing that it has allocated?
Yes. No, I'm sorry. This example was more confusing than helpful. This is how CCured is, right? It's confusing.
So the same fragment would be a problem if they were porting to, say, a 64-bit.
Yes, that's a good point. That's why I claim using CCured feels like porting. It's not automatic. It feels like porting. One more question here. Custom memory allocators. Okay, this is by far the biggest problem in CCured. Not in terms of how many times it occurs, like typically once in a project, but because there's nothing in CCured that can help you deal with that, except to consider the whole buffer from which you allocate various kinds of objects. Consider it as one big area. It's going to be wild unless you allocate the same kind of object all the time. And what we do, the only really good solution we have at the moment is to use a trusted cast. Except if this is a wrapper for malloc, in which case you can tell CCured that this is the case, and it will do the right stuff, essentially trusting malloc. Okay? So all big programs will have at least one trusted cast, if they have a custom memory allocator, which all seem to have. Or at least a wrapper for malloc that prints out I'm allocating memory. Stack allocated buffers or variables. You have a local variable, you stick its address in a global variable or into the heap. That's bad because you can violate safety. So what we give you we can tell that this is going on, and actually we tell it at runtime, because there are runtime checks when you do this kind of stuff that this is not a stack pointer. In general, we can tell it statically. You add this keyword here, and CCured will move the thing to the heap with malloc and free at the end of the function. You can have unions that confuse integers with pointers, and we have a number of solutions there. One that automatically rearranges the union so that pointers and integers do not conflict, growing it. When you can't do that, we have tagged unions, and in some cases, even that is not good enough, and then you have to go in and do something by hand. Casting integers to pointers. This is disallowed for safe pointers. And in fact, if you cast a pointer into an integer and then back into a pointer and try to use it, CCured might let you do all the casting, but when you try to use it, it'll say this is not a pointer. But there are various ways to rewrite the code. For example, instead of this kind of alignment code where you have to cast integers to be able to use arithmetic on it of this form, you can write p plus the aligned version of p minus p. This is perfectly fine, safe pointer, because it's pointer arithmetic. You don't cast. So we have a kind of recipe book like this. Well, this is an actual code that we've seen. You have a buffer in which you put a network packet, let's say, and you have a type that defines the layout of the header and then has this stub for the data. And you might write code like this: buffer, you cast it, pointer to the header, then access the 8th field of data. CCured will let you do this, but this data will have length 1. Right? So you'll get an upper bound error here. So you have to write it as what it is, actually. It's an index into this buffer, not into this array. Right? So many of these things have simple local changes. Okay, a few more slides about how it feels to use it. This is the structure of the tool itself. We take C source files and we merge them. This turns out to be a non-trivial task. We discover lots of bugs in software that doesn't believe in function prototypes, like declaring a function with 3 arguments and using it with 2. The moment you put them together, that becomes very obvious to the compiler. I should point out that this actually, I'm quite happy with this tool, and we have produced one version of the Linux kernel all in one file converted to ANSI C, essentially, which is the input that we need for the inferencer. The inferencer does that linear time scan, produces the browser info, and it goes in and adds runtime checks, and then calls the underlying compiler, which could be GCC or CL, depending of the make file. Okay, how does it feel? What's a typical session of using CCured? You sit down and you change your build process to use CCured. Sometimes it's as easy as changing CC equals CCured. Sometimes, if a big project with thousands of make files, you have to change the configure script somehow. If you have any experience with that kind of build tools, this is a simple thing to do. Then you run CCured, and CCured does complain, rarely, but it does sometimes, about using some variable argument functions or pointers to variable argument functions in certain cases. You fix those errors, typically changing codes, adding some prototypes, and then you obtain a program that fails to link. This is typical. I mean, if you have a program that's larger than 5,000 lines, it will fail to link, almost guaranteed. It fails to link because most often you have lots of wild pointers, so it spreads to your interfaces, and you don't have wrappers for those. So then we sit and we change the code to eliminate wild pointers, doing the kinds of things that I showed in the previous slide. This takes time. It depends a lot on how the code is written. In the end, you touch about 1% of the lines of code. Okay? And that is quite a bit. Because, well, let's see, my students are not really happy to have to change 1% of a 500,000 line program. It's one program that we don't understand. When this is fixed, got rid of the wild pointers, possibly with some trusted casts in there. You still have some failed linking errors, and then you sit down and write wrappers. This is actually working quite well now because we keep accumulating the wrappers we need. And then we run the code and wait for failed runtime checks. And those could either be errors or false alarms, like we see in the example with the buffer and the data of 8. You would get an upper bound and you go in and fix the code. So it's pretty much like porting. We used CCured on quite a few examples. Some of them big. We started with toy programs and the spec benchmarks. We have found bugs in most of these, actually, and we have even used it on a program that's big and C++. And I can tell you more about that if we have time at the end.
I had a question about a couple slides back when you had a fix for the sort of hacky C syntax for having a length and then a buffer inside a structure that was dependent on the length. And your approach was to make, well, a fairly ugly piece of syntax to say you're really going into the buffer and into the structure.
Yeah, I made it even uglier, right?
Yeah. That almost screams for fixing the syntax where we had to have sort of the kludgy char data 1 in order to shut up the C compiler, rather than hacking your syntax. And maybe you might think of fixing the underlying syntax instead.
Yeah. We actually have...
we have a pile of those in Windows.
And we have a mechanism for it. That doesn't work out as well. I wouldn't advertise it. You add an attribute here.
Right.
Say that it's a variable length. And this will go back to wherever this is allocated and will, like here.
Mm-hmm.
And it will carry a length field with it and will do all the right stuff. It doesn't work as well in all cases. It's hard, again, to implement it right because of mutations.
It seems like that's something you want to do anyway when they don't happen to have the same type, right? What if header is saying that what's in me is a batch of 64-bit words as opposed to charge, right? And now you can't just convert the lengths directly; you have to divide or something. Sorry for that.
No, unfortunately, this is all manual right now. The mechanism with the length, we have it in there. We haven't used it as much. We run into all sorts of difficulties to make it work right. So probably the story there is to have a special kind of, this is common, right? Sometimes you put the 0 here, not the 1, but it's common. And we have tried to address that, but the easiest thing to do was, so far, fix the code. This is not...
The compiler bar on 0 is what we have. Isn't there some GCC extension which lets you have char data var size or something like that?
Not to my knowledge. But something quite reasonable to have.
Right? You're suggesting. Yeah, I'm just saying that you're taking that whole char data 1 is a kludge because of C syntax, and then your response to it is to make a piece of C code when you're writing it that actually looks understandable. Yeah, I want the 8th byte of the data, damn it. And then you've changed it to make something much hackier to try to read.
Well,
but it's a hack based on a hack, and maybe you need to go back and look at the original system.
Yes, but you have to understand some of our constraints as well, right? This was easy to do. Changing CCured is so much harder. It's already a big tool. I'm not saying that this is the best solution. Second is in defense of this. This is typically in a macro. And what you see here is the same as before. It's like, get me data at 8. Okay? But, of course, you could do better if you want to put more energy into making the system more complicated. Okay. Let me give you some performance data. This is on spec benchmarks and small kind of point-intensive programs. This is the running time, 50% slower or more time in CCured than the baseline C. 50%, 20%, 80% for LI. LI has a lot of hippified variables. It used a lot of buffers on the stack. And we think that's the reason for that. Purify, I mean, it's in a whole class, different class. It's an order of magnitude. But they don't have as much information as we have. But the interesting thing, we found bugs in 1, 2, 3, not indeed, these are small. In Go, this was playing the game of Go, and they were indexing into different arrays, all in global arrays. Purify couldn't tell them apart. They were next to each other. And it was impossible to tell that this game was playing sometimes not optimally, because you don't expect it to play perfectly anyway. Compressed had array out of bounds. IJPEG had array out of bounds. And this is in spec benchmarks. And they were in cases where Purify couldn't really tell them apart. So the slowdown is, well, sometimes larger than what we hoped it would be. But typically, I think everything now, I think I'm correct, everything is under 2 times slowdown. In many cases, you don't really notice.
So I have a sort of meta comment about this. You mentioned that wild pointers spread everywhere. Part of that is because of the way you're doing your type unification. Did you investigate what would happen if you were willing to clone code and think about what the performance implications could be? Because if I was a compiler writer and I had the slow version of things that uses wild pointers and then a bunch of cases where I'm worried about this, did you think about that kind of issue?
Yeah, there's a keyword in CCured. Clone code, clone data structures. That's how we achieved essentially parametric polymorphism.
Okay.
And we use that sometimes, but we now think it's not quite as good. You can declare a function polymorphic, and it will get instantiated as many times as needed.
What I was worried about was the fact that you have this case, if you have some function and it's called with something that has wild pointers, then the function body itself becomes something that uses wild pointers.
Yes.
And I was more worried about if you were willing to actually sort of have different versions of the function, you could avoid this contamination that anybody else who happens to call this function now suddenly finds their safe pointers turned into wild pointers. That's what I was worried
Not
about.
quite that, but if you declare a function polymorphic, you will get as many copies as necessary, including a 1 wild copy and 1 sequence copy.
A couple of related questions. Is there any good way to identify which sections of the code experience the greatest performance loss due to this? And second is there a way to, say, fragment out this behavior to say, well, I want this section of code to be normal C code because I'm going to intensively review it and I need the performance here?
Yeah, yes and yes. How do you identify? You profile the code before you profile with checks. You can start telling. We have fragmas no box, no cure, which you can use for functions, as function attributes for blocks of code. It's quite messy to implement because these things do talk to the external world. So you have to touch them to adapt the data. Like if they refer to pointer P, and the pointer P happens to be a sequence pointer in the global, you have to change it to refer to P.P. But we have this. It's in the same class with trusted casts. Very rarely used, but useful. So let me now go through a few more slides, and then we can answer the questions. Because I want to get to, some of you might be interested in, what does it take to use CCured on some real code, OpenSSL and OpenSSH? 230K lines of code, 50 hours to cure by a CCured expert, one of us, essentially. 1,700 lines touched. This is no diff between start of the project and end. Many of these are function prototypes. They really do not believe in putting the function pointer arguments in there. They used a lot of char star when they should use really a void star, because this literally for us means a pointer to 1 byte. This means it has different treatment in our system. It uses inline assembly, typically sucked from the include files, and we had to change that into C code. You could also tell CCured to print out the inline assembly but ignore it. We had to put in the lots of RTTI pointers. We ended up with 2 trusted casts in the library, in SSL, which is smaller. I think it's only 70K of this. Or no, the other way around. I think it's 140K. 14 trusted casts in OpenSSH. They cast between different versions of socket adder. We found 3 bugs. Printf. Our system has a pretty sophisticated way of handling variable argument functions and has special cases for printf. So it finds some bugs quite a compile time. Find a buffer overrun, bug in using open. Depending on the test case, between 1 and 80% slowdown. 80% is in compute intensive, crypto kind of stuff. 1 is if you're doing any I/O, all of the checks we're doing is essentially shadowed. We run Valgrind on this, not Purify, I think for some technical reasons, and it's quite slow. Valgrind is like Purify, actually. Does the same thing, but it's free. SendMail, 100K lines, 20 hours to cure, 200 lines changed. The same kind of issues, some stack buffers moved out, some unions, we had to kind of rearrange them so that pointers don't conflict with integers. We ended up with 4 trusted casts. Okay? There's typically a direct connection between how many hours you're willing to spend on it and how many trusted casts you have. We found 2 bugs. We're out of bounds. Of course, we verified the bugs that are out there known. 46% slowdown. Is this acceptable for your mail machine? I don't know. I should say we can do a lot better in optimizing the checks than we do at the moment. Bind. This is doing DNS in 330,000 lines of code. I don't know what's in there. A rather lazy graduate student. It took just 5 hours to change 88 lines. Put in, so 530 bad casts initially out of 82,000. RTTI, so some of these were downcasts, 20% of them. You put in RTTI, some of them go away. 380, the student just wrote the script to mark as trusted cast. It's really ugly code. We haven't found any bugs. 80% slowdown with this. But I think it's not that bad. Here's where you have to start if you want to verify bind manually.
Now, is it likely? Let's just suppose there were bugs in there that's not perfect code. Is there a relationship between the number of bugs you find? An inverse relationship between the number of bugs you find and the number of casts you mark as trusted?
No. The trusted cast cannot possibly fail.
Right. Since they can't fail, you wouldn't find the bug.
Right, but you'd find it down the road. Actually, the trusted cast is not correct. You'll find it down the road as a false alarm most often because you didn't set the metadata right, and some checks will fail. Like this pointer appears to be safe because it made it trusted, but you then cast into a sequence for arithmetic, and when that does, CCured puts a bounds of 1 on it and fails. Here's why we didn't find bugs. We were pretty bad at the beginning of this project to realize that we should cure projects that we can run. Okay? We cured SendMail, we cured Bind, we ran 3 test cases on each. Because we couldn't convince really anybody to use SendMail in their environment. Not yet, anyway.
So how many false alarms do you find?
How many false alarms?
For all these trusted in all the cases.
Few, and we have a way of specifying, ignore this thing. Typically, if you have a false alarm, like 1 bounce check fails all the time. Very few. I don't know. We find few bugs, so few alarms total. And
yeah, I was just concerned. You have 2 bugs and then maybe 100 false alarms.
No.
Not very good.
No, but maybe 2 false alarms as well. But we're talking about small numbers.
You mentioned garbage collection. What about the problem of freeing memory and it's still being used after being freed? That's a way of violating type safety.
Right. So we use the Boneweiser collector in the default configuration, which could turn off. But there's another. Notice that when we get out of the custom allocator, we use a trusted cast. This allows us to treat the different pieces that come out of the allocator as independent objects. But it also means that if your internal custom allocator is not correct, you're going to violate type safety. And the way this is going to show up most often as a false alarm.
So do you eliminate calls to the free routine in the library?
Yeah, so when you plug in the Boneweiser collector, the free becomes a no-op.
Did your performance statistics include the Boneweiser collector?
Yes. Okay. Really, I think it's dwarfed for these benchmarks by our checks. It's really good piece of code. Apache, almost 300K lines of code. 2 months is still going, but it's an undergraduate who's learning, turns out, Make at the same time. So far, we changed 550 lines of code. 50% of the pointers were saved, 47% while day 1. That's how we started. 1,900 bad casts, and this student in 2 months, changing 550 lines, essentially got it down to 470 trusted casts, where we kind of gave up. But there were things like this. I mean, Apache is really aggressive in how they use. If you wonder what this code is doing, is it's taking a pointer to a structure and indexing backwards. If you can't express with the C-type system, it can only go forwards, accessing fields of structure. So they would like a reverse struct for this, and I don't know why. We are not yet linking this thing. Okay, and here's a particular example from the small end of the spectrum. Somebody sent us email. I have a 5,000 line web server. Please do it. Matt sat down 3 hours to cure it. 30 lines changed. 25 bad casts initially, 10 bad casts, they were missing functional prototypes. So CCured took some conservative approximation of those. Was using a pointer a function which we haven't encountered before, so we had to declare it as a printf function and had to write a new wrapper. We found one buffer overrun error, code like this, allocating 255 bytes and using max fat here. You probably seen things like this.
You've never seen that before.
No, not yet. Okay. But here's actually the thing that's most promising about CCured. And I'm just about to get a test along these lines started with some undergrads. You should write new code with CCured. It's not heavy to just think about whether you're ever going to do arithmetic on this point or not. You write sequence there. And if you do this for all of your globals, the inference can easily handle your local variables and get very good reports, error reports, and traces in that case. You don't have to merge the program anymore. You have separate compilation. It's also, I think, just good software engineering. But I really don't have experience of how heavy it is. You would have to avoid those things that I had on those slides. You'd have to program around them from day one, because CCured will complain right away. But it should be easy to evolve. And by the way, SSL, it took 50 hours to cure, and then 1 more hour to port the patches, the new release. So it's easy to maintain incrementally. To conclude, I think, and I still believe, that C programs are mostly type safe. You just need a type system that can see the type safety in a C program. Okay? And you need to use runtime checking to handle those cases where static checking gives up. But it's not that bad, and we can probably do better. CCured is not automatic. It does feel like coding, and well, about 1% of the lines you probably have to touch. Probably end up with 1 in 1,000 trusted cast. You don't want to spend too much time redesigning. So I think that overall, you can prevent security holes at reasonable cost. And so I invite you to go and visit the CCured website. You can even send C code over, and you get back the cured code. You look at the checks that end in there and play with the system.
We can.
Yeah.
But then we have to kill
couple of questions. One, I was wondering if maybe there would be some benefit to enabling a mode where this was checked only in debug or a check build, or and optionally, so that I could go ahead and do my testing with and take the perf hit in that area, and then go ahead and go full perf for release, where I obviously wouldn't get my benefit, but it would help me more rigorously find bugs during testing. The second is, I wonder how well something like this would work with code analysis tools, and I wonder if a code analysis tool could work better with cured code than regular code.
Okay, so my answer to the first question is, I think, obviously, yes, nothing prevents you from having 2 builds, one enabling CCured and one disabling it. But it's really, honestly, something I want to avoid. And we want this to be run on production code whenever possible. Because that's when you get the benefit. It's when you get the actual, load of the program that you will see these errors. And that's why we're not finding bugs in SendMail, because we're not running it. We're running it in the lab on the 3 regression tests they have. I believe we would find bugs in SendMail if we were to run it. The answer to the second question, actually, what was that?
Well, I wonder if
combining with code analysis.
Combining with code analysis.
Clearly synergy there. This information is useful for all kinds of analyses.
It is useful, but in truth, higher level analysis assume this information. Assume the pointers are type safe and go from there. So it would make those analyses sound. Whether this computes essentially a weak form of pointer analysis. Pointer analysis.
Now here's a somewhat rude question, given that this is based on the assumption that I'm going to be writing in C. But fully leveraging C++, and what I can really do with it, if I'm sitting down to write new code, why would I do this when I can just write in, completely normal C++ and get the same benefits if I use things like STL arrays and that type of thing. Now I've got my bounds checking.
I personally don't believe that. I believe you can go a long way towards getting your bounds checking, but just because STL is very careful about its bounds checking, it doesn't mean you will do the bounds checking right. Okay? So the answer with C++, it's really an engineering question. I mean, there's nothing in C++ that prevents us from doing this kind of stuff except an order of magnitude more students, essentially, to work on it. And actually, I sat down and started on the C++ front end only to learn that it's really an order of magnitude more work. Now, we did apply this on C++ code. Here's what we did. It's not ideal. We don't recommend it to friends. Run EDG on it, convert it to C. So amazingly clean C comes out of it, except for the parts where they implement virtual method dispatch. We wrote a 5,000-line pattern matcher, essentially. It goes over the code and separates those messy stuff into the part that's type safe, and using a number like 10 trusted functions to do the dispatch. And we apply CCured in the resulting code. On a million lines of code, 3 times fewer bad casts than a regular C program, because you don't need to cast as much in C++. Except for the engineering of actually using it and having this EDG convert to C and all that. This works in C++ in principle. I just don't have the tool to really give you to use it today.
Hey,
sorry.
First.
You had a hand high.
I'm following too. Have you investigated systems code where one problem with systems code is that data can be in the wrong place and you can cause a page fault, maybe your program's running in a higher, or your thread is running in a higher priority than the code that's pulling the pages in.
Right. So we have actually done a couple of Linux device drivers. As you expect, there will be uses for trusted casts in there in inline assembly. In that sense, we're not completely sound. But it works perfectly fine because, again, most of the device drivers perfectly fine C code, except where it really needs to argue stuff. And that would end up either, say, don't box this block of code, or trust this cast, or something like that.
But the extra bits of data you're adding to the structures, do you put them in a place that they won't cause page faults?
We were able to do it. Well, they are with the data right now. So ignoring that separate metadata stuff, they are in the same place with the data, just interspersed with the data. And for device drivers in Linux, we're able to keep the interface with the rest of the kernel clean and keep kind of the metadata for us, and it worked perfectly fine. And of course, we didn't see like network drivers, file system drivers. We didn't see any performance hit because the I/O completely dwarfs these. Sorry, Rustam.
Go ahead.
Suppose that you were that you make the decision, well, you want to save code, so you're going to use, let's say, CCured. So then you need the while pointers when you communicate with various libraries, because the libraries give you back buffers like the one we've shown. But other than that, would the programmer ever use the while pointers? I mean, would the programmer ever think, here's a good application of the while pointer, let's use that?
Good application of the while pointer is if you want to cast without thinking, which you need to do when you come out of an allocator, for example. There's no way around it.
Yeah, so that's the library issue again, right? So if you have an allocator and you suppose you had a library that gave you back, different things, then it seems to me that you would never use the while pointers, which is quite interesting because you started off by saying that people use a language like C because they think that they would like better performance. But in fact, it's the while pointers that cost. And now it seems even that there's no reason for using them.
Yeah.
The other things that you're getting are actually things that exist in C#, for example.
There are reasons to use them, though. For example, if you're playing with ICMP packets on the network, all you know is you've got a data blob, and first you say, well, is it really an IP header? Yeah, it's really an IP header. Now where's my ICMP header?
No, but I would point out.
So I think his point is it's more than just the library; it's the existing data formats as well, not just libraries.
Right. I mean, if you call any kind of API that's going to give you back such a variable structure, you typically give it, a big buffer, or if you get it, as you said, from the network. But if we isolated those into something that's takes those buffers that come from the network and pick them out and piece them apart into safe data structures, then it seems that there's absolutely no reason to use a language like C anymore. Thank goodness it's
well, let me try to answer some of those. Do you have to use wild pointers? Of course not, because if you could write the same application in C#, you don't use wild pointers.
Right, but would you like to? I mean, is there some
I would like to. That's what I said. We changed the parser line to actually port the code so that it doesn't use wild pointer. And because can't afford to really rewrite it all, we have to use trusted cache. But in principle, you would program in a style that resembles C#, but maybe with a few more features like point arithmetic you can use freely. Because CCured converts point arithmetic into arrays, essentially. Carries the beginning of the array. It converts your program into C# if you want. While you use C. And the part with ICMP packets, there are no pointers in ICMP packets. Or if you don't have pointers in there, it's all a matter of bounds, array bounds, no need for wild pointers. It's all sequence pointers.
Well, yeah, what you've got is essentially this. It boils down to a massive union. There's a couple of things you can depend on that are at the bottom of the packet, but then from there on, it could all be data. Who knows? Yeah,
but typically those unions, those don't contain pointers in there, the headers of the various kinds of packets. So
the last thing you've got is a char pointer to data. That's the last thing you've ever got on an ICMP.
Okay, but that doesn't have to be a pointer. It can be an offset.
Better not be putting pointers go across the net. Although we've seen it.
But that's true.
But you can imagine, somebody doing that and then you need wild.
So just to make it clear, what you're really proposing is that we extend C with these no notions of pointers, and that we essentially have a different version of C, a changed language that allows us to write more precisely safe code.
Yes, that's a fair way of putting it. We also give it this inferencer. We'll try as hard to convert C to... Yeah.
So another question. So you started out saying that most of the C programs are actually sort of doing things right. They're sort of correct. Okay. So if you have a C program that's doing things right, then usually you actually pass these buffer bounds around yourself, right? Because otherwise, how are you going to get it right? And so your addition of this metadata is sort of redundant with the actually good C program already. So have you looked at that? I mean, how you take advantage of
we have looked. So essentially, the issue is that remember the read, we passed in the length, the program passed in the length, and we passed our own length.
That's right.
Okay? The reason is it was the easiest way to ensure that the length is accurate. Okay? Otherwise, you go into dependent types, where the type of the buffer depends. Dependent types in the context of imperative programs are very, very hard, because how do you prevent changing the length? Like, imagine you have a structure with two fields. One is the pointer, one is the length. Okay? Are you ever going to update the length? Well, if you update the length, why do you update it? Do you shrink the buffer? Do you want to write another one? Which one you write first? There are issues like that, which are more than we wanted to handle. But that's probably the next way to extend the language specification mechanisms like that.
Of course, those kinds of changes are usually done intra-procedurally, right? Which should make it easier in an imperative language, right?
But you are now going in a direction which we didn't want to go, like, let's have something that works sometimes. Okay? What we have works pretty much, and carrying this metadata with pointers was pretty much all the time. And maybe it's now time to go into those special case solutions, which will handle probably most of the cases.
I wonder how much traction you could get in a C++ app by taking all the pointers and basically writing a set of smart pointer classes that mirror your types, and then substituting them in and implementing the checking that way. I work in Office, and we have things that are written in C, and we have things that are written in C++, both. So, I've got to look at both problems.
I see. So I guess your question is, if I take the C++ pointers and I replace their type with one that does checking and carries all this data, and then you overload it.
Yeah, there's there's a whole bunch of different ways. It's a religious argument to a large extent of how to properly implement a smart pointer type. And the most basic thing you can do is you can make sure that whatever gets allocated also gets free. But there's other things you can do with it as well. One of the things that this made me start thinking about is I could make a set of 4 different types of safe pointers that mirror your types and do the same types of checking, and that if I did that and then implemented that thoroughly throughout my application, then I might be able to get a lot of the same benefits.
But you're talking about an alternative way to implement the checks.
Yeah. Well, I'm thinking of, this is a great idea. How can I apply it to a C++ application?
Probably the best way is to sit down and write a front end for C++ that can work with our stuff. But
we already have it. We know that's arbitrarily hard. So
this is one thing that our front end does. It simplifies our life a lot. We distill C into a mini C, a simple form of C, on which our analysis can analyze and transform. So easy to transform. And I don't think anybody else has quite that level of simplification of C. And that's what's hard for C++. We have parsers. But after syntax trees, to start doing the transformations that we need to do, maybe the analysis we could, is to get it a little bit long. But the moment you start changing the code, then you need to be really precise.
So is the issue with the sort of EDG lowering based approach, are there some high-level semantics that you lose as a part of it and have a hard time recovering? Because we did a similar thing in prefix, and rather than trying to recover after the fact, we wound up modifying the EDG lowering to just do things more selectively.
We don't lose anything that CCured means.
Okay.
CCured is just type correctly. Right? The person who loses is the programmer, the person who's using the tool, because CCured complains about something that probably never seen.
So why don't we wrap it up here? Say that George is going to be around this afternoon. If people want to follow up further with him, he has some time available. So let's thank the speaker.